Hey there, glad to have you back with me again. Today we're going to learn two more convergence and divergence tests, the alternating series test and the ratio test. An alternating series is a series whose terms are alternately positive and negative, like this guy. And if I were to show you the nth term, it would be the harmonic series, but this front part is a negative one going back and forth from negative to positive, depending on what n we're on. I could also write it like this. We still have the harmonic series, but this one just has an n instead of an n plus 1, which basically is just telling you if the first term is positive or if the first term is negative. And then it just alternates positive, negative, or negative, positive, negative, positive. So that's what an alternating test looks like. It could also, the nth term could also look like this. Whoa. I'll show you how that works a little bit later. So the alternating series test for convergence is this. If a sub n is positive, then the alternating series converges if both of the following conditions are met. 1, the limit as n approaches infinity of a sub n equals 0, which makes sense. Otherwise, it would diverge for the nth term test. And 2, the absolute value of a sub n plus 1 is less than or equal to the absolute value of a sub n for all n. So the terms are never increasing. Now, a note of caution, if the limit as n approaches infinity of a sub n doesn't equal 0, you don't get to say that the series diverges because of the alternating series test. Like I said, it diverges because of the nth term test. So be careful. Another note, how do you know that the next term is less than or equal to the term previous for all n? Well, sometimes it's obvious. Sometimes they tell you. If they don't tell you and you need to know, you can take the first derivative and see if you have a negative or positive first derivative. So sit back and let me just show you how an alternating series would converge. So given the harmonic series, we've looked at that before. That's a p series, and it diverges because p equals 1. Now, what if you wanted to have the signs alternate on each term? What would you have to do to this a sub n to make that happen? Well, you have to add an alternating 1 to negative 1 thing before that. And that would give us 1, negative 1/2, positive 1/3, negative 1/4, and so on and so forth. So if we start taking partial sums, the first partial sum is 1. And I'm going to mark that on my line here. Let me clean this up again. The second partial sum, 1 minus 1/2, is 1/2. The third partial sum is 5/6. The fourth partial sum is 7/12. The fifth partial sum is 47/60. Do you see what's happening here? It's getting really, really close to something around here. It's converging to something. So we would say that this alternating harmonic series converges. So let's practice this. Determine if the following series converges or diverges. Okay, well, first of all, do we know that it's an alternating series? Yes, we do, because of this negative 1 to the n plus 1. Is the limit as n approaches infinity of a sub n equals 0? So just looking at this, does the limit as n approaches infinity of n plus 5 over n plus 2 times n plus 3, does that equal 0? Well, that's basically asking n over n squared. And so, yeah, that goes to 0. So we've got the second condition met. And then this one I think is kind of hard. Is the next term less than or equal to the one previous to it? And yeah, it is. But we would say a sub n is non-increasing. And I don't want to say it's decreasing because sometimes they can be equal to. See that? So it's not increasing. Anyway, we've got all these three conditions met, and so the series converges by the alternating series test. Let's try another one. Do we have an alternating series? Yes, we do. The limit as n approaches infinity of a sub n, does that equal 0? No. Okay, so this diverges by the nth term test, and that's the end of that problem. Oh, I told you I'd show you this one. Cosine pi n. What does that mean? Well, cosine of pi is -1, yeah? What about as n increases here, what's the cosine of 2 pi? It's 1. What's the cosine of 3 pi? -1. Do you see what's happening here? So we do, in fact, have an alternating series. This cosine pi n makes it an alternating series. Is the limit as n approaches infinity of a sub n 0? Yes, it is. Is it a non-increasing function? Yes, it is. So this series converges by the alternating series test. The ratio test. This one looks crazy, but I kind of think it's fun. This is really a great one for complex series. And what it says is, if we have this infinite series of a sub n, it has positive terms, and if you take the a sub n plus 1 term and divide it by the a sub n term, and then take the limit as n approaches infinity, and you get a number that's less than 1, then the series converges. That sounds terrible, but it's actually cool. If you do the same thing, but as you take the limit as n approaches infinity and you get something greater than 1, then the series diverges. If it equals 1, you got to use another test. So let me show you how this works. This is a complex nightmare. So you've got n as a base. You also have n in the exponent. This is a perfect time to use the ratio test. So our original thing right here that we're looking at, that a sub n, we need to figure out, well, what would the next term be? What would the a sub n plus 1 term be? So we take each of the n's and add 1 to it. So we've got n plus 1 squared, n plus 1 plus 1, 5 to the n plus 1. We clean that up just a smidge. We've got n plus 1 squared times 3 to the n plus 2 over 5 to the n plus 1. All right, now we're going to divide that by a sub n. So we've got a sub n plus 1 divided by a sub n, which means we can multiply by the reciprocal of a sub n. Now, it still looks like a bit of a nightmare, doesn't it? But let's take this first term and clean this up a little bit so we can see what's going on. So 3 to the n plus 2, that's 3 to the n times 3 squared. And 5 to the n plus 1 is 5 to the n times 5. Now, if we continue on and multiply that by the reciprocal of our a sub n term, we get to cancel some stuff out. See those 5 to the n's? Gone. 3 to the n's? Gone. 3 squared divided by 3, well, kind of gone, right? So what we end up with is 3 times n plus 1 squared over 5n squared. Well, the limit as n approaches infinity of that is 3/5, which is less than 1. So this series converges by the ratio test. Here's another one. And again, it's complex because we've got an n as the exponent, and then an n factorial. Oh my goodness. So again, we start with our a sub n, then we have to create an a sub n plus 1 term. Now that n plus 1 factorial, we did this in the last lesson, that's the same as n plus 1 times n minus 1 times n minus 2. And this whole section here, well, that's the same thing as n factorial. All right, so let's rewrite that. Our n plus 1 term is 4 to the n times 4. I just rewrote that so I could see it a little bit better, over n plus 1 n factorial. Then I'll multiply that times the reciprocal of my a sub n, and then cancel some stuff out. The n factorials are gone, the 4 to the n's are gone. So we take the limit as n approaches infinity of 4 over n plus 1. That's 0, which is less than 1. So my original series converges by the ratio test. All right, here's another one. We have our a sub n term, but I need you to be really careful when we find the n plus 1 term, because if we have 2n on top and I need the n plus 1 term, the n plus 1 term is not 2n plus 1. You don't just get to tack a 1 on the end of it, because basically it's 2 times n. So we need to do 2 times n plus 1, which is 2n plus 2. So that's something to just watch for. We've got 2n plus 2 factorial over n plus 1 to the 5th. Now we've got that 2n plus 2 factorial. So let's just see what's going on with that one. That's 2n plus 2 times 2n plus 1 times 2n, and so on and so forth. And from here on out, 2n and down, that's the same thing as 2n factorial. So we'll rewrite that as 2n plus 2 times 2n plus 1 times 2n factorial all over n plus 1 to the 5th. And we'll multiply that by the reciprocal of our a sub n term. And then is there anything we can cancel? Yep, the 2n factorials cancel. That's it. So now we'll take the limit as n approaches infinity. And wow, we've got a lot of n's going on up here. So this one's heading towards infinity. So that's definitely bigger than 1. So this diverges by the ratio test. And that's that. Like, this one looks complicated, but I just think it's fun to kind of rearrange things and then just hack at it, like just cross things out. So anyway, okay, have a great time practicing these, and I'll see you on the next lesson.